So in this session, we're going to talk about the last of the different types of dead stars. The black hole are definitely the most well-known and the most extreme case of stellar collapse at the end of a star's life. Again, I do recommend using the dead star memory matrix that's available on both Blackboard and Lon Kappa to kind of organize some of the information about these types of dead stars and be able to quickly do compare and contrasts between these dead stars. So for these black holes, if the core that's collapsing is more than 3 solar masses, then there aren't really any known forces that can prevent this object going through complete and total gravitational collapse. By complete and total gravitational collapse, I mean that, at least according to classical physics, things get a little bit different when we talk about quantum mechanics, which we're not going to worry about for this course. But at least a classical picture of black holes is that the mass of the black hole actually collapsed down to 0 size. This object would have infinite density because we've got some amount of mass collapsed down to 0 size, and we call this point the singularity. So the singularity is the point of 0 size right at the center of the black hole where all of the mass has collapsed down into. So the point where all of the black hole's mass collapses down to. And this singularity would be a point of infinite density. Now, for kind of full disclosure, there's a lot that we don't know about this. Right now, the two main ideas in physics, general relativity and quantum mechanics, we can't really mix those together in a way that allows us to describe what the center of a black hole would be like. So we are going to be looking at this kind of classical picture. It's not entirely accurate, but it's a good enough approximation of some of the key ideas about these black holes. When we talk about a singularity, basically it's a point where our understanding of physics breaks down, these points of infinite density. We don't know what would actually happen under these conditions, so we just kind of call it a singularity. Okay. What we often talk about in terms of the size of a black hole is a region called the event horizon. So let's talk about that briefly. So the event horizon, this is the region where not even light would be able to escape the gravitational pull of this black hole. So it's the region where even light could not escape. This one wouldn't be 0 size. A couple of things about this. When we talk about a horizon, if you think of the horizon on the Earth, it's kind of the limit that you can see because the curvature of the Earth is kind of bending away from you. So there's a limit as to how far you can see before you're looking at the horizon. You can't see any further away than that. The event horizon is kind of similar because even if something was on the other side of that event horizon, was trying to give off light, that light would not be able to escape the gravitational pull and would just be pulled back in towards the singularity. So this region, we can't see past there, just like we can't see past the horizon on the Earth. In this case, that's why we call this an event horizon. So basically, the event horizon, it is a one-way path. if you go past the event horizon, we are not going to see you again. We'll talk briefly about what might actually happen if you were to cross that. And again, the density of this black hole, if we're talking about the singularity itself, we're saying all of the mass of this black hole has been compressed down into a point of zero size. So when we're talking about the density, we have the mass of the leftover core of the star that was collapsing, and anything that has fallen in since, divided by this volume that shrinks to zero. And that's why this density, again, in the classical picture, goes to infinity. Not because the mass of the black hole is super, super large, but because that material has actually collapsed down to zero size. So a massive object with no volume is a singularity of infinite density. Black holes do not have infinite mass. Going back to the equation for the gravitational force, which, again, if you're getting close to a black hole, we actually need to use general relativity instead, but this still gives us a good enough picture. When we're talking about the gravitational force between objects, it depends on the masses of those objects and the distance of those objects. These black holes, they're not infinite mass. The mass is just whatever the mass of the core was that collapsed, plus anything that's fallen in since. What makes the black hole's gravity so strong is that you can, again, get very, very close. If you are far away from a black hole, it will act just like any other massive object. As far as gravity is concerned, there's no difference if we replaced our one solar mass sun with a one solar mass black hole. If you replaced our sun with a black hole of the same mass, again, our sun isn't massive enough to become a black hole, but if you could magically switch out our sun for a black hole, Earth and all the other planets would keep on moving in their orbits that they already have with no effect to their orbits. Of course, the fact that we're no longer getting light from the sun to heat our planet and provide us energy would mean that we are all going to die, but don't worry, the orbit of the Earth would be just fine. So again, black holes do not have infinite mass. If a black hole did have infinite mass, then no matter what other object it was interacting with, that gravitational force would be infinite and everything would be immediately sucked into a black hole, even if it's on the other side of the universe. So again, these black holes do not have infinite mass. The gravity only gets very strong if you're very close to them. Further away, they act just like any other massive object. Again, if we replaced our sun with a one solar mass black hole, the orbits of the planets would keep on going in the exact same way that they are right now. Now, again, when we have one of these objects that's collapsing and the gravitational force is getting stronger and stronger, we talked about a little bit about the escape velocity of certain objects, saying the stronger the gravitational pull, the faster you'd have to be launched off that object in order to escape that object's gravitational influence. We said for white dwarfs, this is around 2% the speed of light. Compressing it down more into a neutron star, for neutron stars, the escape velocity from the surface is around 70% the speed of light. For these black holes, they've collapsed down so much that even light, the fastest thing in the universe, can't escape their gravitational influence if you're close enough to them. So again, this event horizon is defined as the point where that escape speed becomes the speed of light. If you go inside of that event horizon, not even light can escape. And again, light is the fastest thing, the fastest that any material object can move in the universe. So it's kind of an abandon all hope ye who enter here, if anyone remembers their Dante. But that escape velocity, there is an equation for it. We're not going to worry about it too much. But basically, the larger the mass of the singularity, the larger the mass of this black hole, the greater the radius of the event horizon. And in fact, there's actually a fairly simple equation for this. The radius of that event horizon is called the Schwarzschild radius, and this depends only on the mass of the singularity. Again, that mass of the singularity is just the mass of the star core that collapsed plus anything that's fallen in since. And this Schwarzschild radius is given by the following equation. Let me get rid of this. This Schwarzschild radius in kilometers is basically just 3 times the mass of that black hole in solar masses. The higher the mass of the object, the larger that event horizon radius is going to be. So there are a whole bunch of strong candidates for black holes, things that are almost certainly black holes. Cygnus X1 was the first one that was kind of detected with high confidence. And again, there's all sorts of these black hole candidates in binary systems. So these are black holes in a binary system. So there's an ordinary star and a black hole in orbit around each other. Again, a black hole, if you're far enough away from it, it acts just like any other gravitating object. You know, you can orbit around it just fine. It's only when you get very, very close to the black hole, and specifically inside the event horizon radius, where you are not coming back from that trip. So for example, if the black hole in Cygnus X1 is 10 solar masses, well, in this equation, that mass would be 10 because we're measuring it in solar masses. So multiply that by 3 and we'd get 30 kilometers for the event horizon radius. Again, this would not be very far. 30 kilometers is about, you know, a little under 20 miles. So it's only if you get very, very close to these things that you have that event horizon, that point of no return. Well, just like the other objects, if a black hole has no companion star and is not accreting any material, well, it's basically just going to sit there and remain unchanged. And in fact, if it's not in a binary system, it's actually really, really hard to detect. If it's not accreting any material and it's a black hole, it's not giving off any light on its own, it's very, very difficult to detect. There are some methods that we can use if, you know, we're lucky with the particular circumstances of this black hole. But we'll talk about those a little bit later on in the course. But if there's no companion star, it's just going to sit there and remain unchanged after that point. But like our other types of dead stars, if it's in a binary star system and that companion star starts going into, say, a red giant or a supergiant, starts puffing up its outer layers, if some of those outer layers get a little bit too close, this black hole is going to start to pull in some of that material, make one of those accretion disks. Again, those accretion disks will tend to heat up as material rubs together. And even though we can't see the black hole itself, we can detect the very strong amounts of radiation, and especially X-ray light, that is given off by this superheated material. Material heated to can be millions of Kelvin. It's kind of like saying this: black holes are invisible. They do not give off light. So how do we detect them? Well, for example, how do we detect whether it's windy? If I were to look outside and I wanted to know whether or not it was windy, how might I detect that? Well, if I see tree branches, you know, shaking around strongly, or if, you know, there's a flag or something outside and I see that flag flapping, I can detect the wind based on its effect on objects around it. Same kind of thing for black holes. We can detect black holes by their gravitational effect on nearby stars, or if they're pulling material into this accretion disk, that's going to heat up that material. And this accretion disk, that hot material, is still outside of the black hole, so we can still see the light from that material. A little bit of history stuff. The first black hole discovered is Cygnus X1. And again, we detected it by its really, really strong X-ray emissions in 1964. This black hole is somewhere between, like, I think it's like 8 to 16 solar masses, and it's got this companion star that's orbiting around it. It's accreting material, and that material in that accretion disk heats up and gives off lots of X-rays. So this is an actual X-ray image of the system. This is kind of a computer simulation of what that accreting material might actually look like. So yeah, that bright X-ray source is the accretion disk around the event horizon of that black hole. This slide might no longer be accurate because there are some candidates. This hasn't been confirmed yet, but there are a couple of black hole candidates that are actually a little bit closer than this. But this is one of the nearest black hole candidates, V4641. I know, catchy name, but it's about 1,600 light years away, and it was detected by its X-ray emissions in around 1999. Again, this is the artist conception, and this is the X-ray image. We see that material. This material that's being pulled in and spinning around very rapidly and heating up, becoming more energetic, kind of like the jets that we talked about expanding off of protostars. The material in the accretion disk around these objects can start to heat up, generate very strong magnetic fields going in a north and south direction, and some of these charged particles can be caught up in those magnetic fields and actually be jetted off of the region around this black hole. So nothing can escape from within the event horizon of a black hole. If you cross that event horizon, nothing's coming out of there. But again, the parts of the accretion disk that are glowing that are still outside of the event horizon, we can still detect those parts. And like I said, similar to what we saw with protostars, these spinning heated disks of charged particles produce strong magnetic fields and can produce these jets of material. This is still outside of the event horizon. I can't tell you how many science articles I've seen that say something like, oh, we've detected this jet coming from inside of a black hole. This jet coming out of a black hole, implying that it's actually coming out of the event horizon. That is not the case when you actually read the articles that those cite. We're talking about a jet being produced outside of the event horizon and just escaping from outside of the event horizon. So if this is the event horizon and we've got the disk of material around it, that jet is still staying outside of the event horizon. It never actually passes into the event horizon before being expelled outwards. So these accretion disks around neutron stars and black holes, well, it would actually be hard to get shots of it this accurate, but for the accretion disk around a black hole, the center would be dark. For the accretion disk around a neutron star, as material violently falls onto that, we get these X-ray bursts. For the neutron star, we'd actually be able to see light from the surface of that neutron star. We are going to be talking later on about supermassive black holes. Supermassive black holes that were probably formed in a way other than through a supernova. If you've seen in the last couple of years, we've gotten a couple images of the regions right around these supermassive black holes. We'll talk about those in more detail when we talk about some of the properties of galaxies. So the last thing here is what were to happen if you were to fall into a black hole. I would generally advise against this because there's a couple of things that are going to happen. When you cross the event horizon, it's possible that if we're talking about a large enough black hole, when you cross the event horizon, you might not even notice anything crossing the event horizon. Even though once you've crossed the event horizon, it's not going to take long for you to die. But when you cross the event horizon, you're not going to notice anything at that particular point. But here's what's going to happen. The gravitational forces are going to get stronger and stronger as you get closer and closer to the center of that black hole. So let's say this is the singularity, and you are falling in feet first. And let's just write down our gravitational force equation. Again, if we're talking about black holes, this equation isn't quite super accurate, but it'll still get the general point across. So when you're falling into this black hole, your feet are a little bit closer to the singularity than your head is. Well, if your feet are a little bit closer, then your feet are going to be being pulled towards the black hole more than your head is. Now, this doesn't just happen for black holes. This happens on the Earth as well. If I were to stand up, my feet are closer to the center of the Earth than my head is, so my feet are being pulled a little bit more. But under ordinary circumstances, my bones and muscles and all the forces that hold, molecules together in solids, those forces are more than enough to keep me whole. The problem is that as you get closer and closer to the black hole, the amount that your feet are being pulled on increases way, way faster than the amount that your head's being pulled on. So these differences in forces are going to get stronger and stronger and will eventually rip you apart. So the forces on my head are less than the forces on my feet. So I'm going to start to be stretched out and eventually ripped in half. So then we're going to have half of my torso falling into the black hole. So let's say there and there. So let's say my legs have been ripped off already. But now my stomach is closer to the black hole, so it's being pulled more than my head. And eventually that will rip that part in half. And now I'm just the head. My chin is being pulled more than the top of my head. Eventually that rips apart all the way down to the atomic scale, where I'm now a stream of atoms. And for this atom, well, this side of the atom is a little bit closer to the black hole than this side of the atom is. And eventually I get ripped apart down to a subatomic scale. The technical name for this method of death that no one has ever experienced, because no one has actually fallen into a black hole, is called spaghettification. So again, my general advice is to, if you have the choice on whether to jump into a black hole or not, probably go with a no on that one. So again, these are the different types of dead stars. I do again recommend using that table, that dead star memory matrix, to try to list out some of the key pieces of information and be able to compare and contrast between these different types of dead stars.